This is Euclid Book 2, Proposition number 10, Part 3. And I know by now you're probably sitting there going, wait a minute, is this proof ever going to end? And you know what? I'm sitting here going, I don't know if it ever will, but we're going to get through it anyway. Alright. First of all, I want to show you some right-angled triangles, which you should have noticed right off the bat when you were starting this proof. We have a right-angled triangle that starts with letter E, goes down to A, and goes over here to C. We have established in the proof already that the sides EC and CA are equal in length. Therefore, the angles AEC and the angle EAC are equal in size, and they actually end up being 45 degrees each. Okay? Now, we have another right-angled triangle. It starts with letter E, comes down to C, and it goes over to B. And, of course, because EC is equal in length to CB, then, of course, these two angles right over here are equal in size, and they both happen to be 45 degrees. But there's another right-angled triangle. It starts at letter G, comes up to E, and goes over to F. And this is a right-angled triangle, and of course there's an angle here and an angle here, and they're both 45 degrees and they're equal to one another. But yet there's another right-angled triangle. It starts with letter D, goes over here to B, and comes over here to G. And of course these two angles right over here are equal in size, and they both happen to be 45 degrees. But yet there is one more right-angled triangle. Starts with letter G, comes over to D, and goes all the way over to A. Alright, now we don't know all the facts on this triangle yet, but we're going to get there. But there's also a parallelogram, and you should have noticed this by now. It starts with letter C, comes up to E, goes over to F, and comes down to D. Wow! I can tell you right now, that is a lot of information to remember. Alright. Now, do you remember back in Euclid Book 1, propositions number 46 and 47, where we started forming squares out of sides of triangles? Okay. We have a triangle here. It starts at letter E, goes down to A, comes over here to C. It's a right-angled triangle, which means we're going to start being able to use Euclid Book 1, Proposition 47 on it. First thing is that the area, now let's say we were to take line EC as one of the four sides of a square and form the other three sides of the square the same length as EC. The area within that square, if we were to draw it out, would be equal in size to the same square. Let's say we drew another square and it started with point A, came over here to point C. That was one of the sides of the square. Then we made three other sides, and they all were equal in size to line AC. Okay? The area contained by that square would be equal in size to the area contained by this square over here. And because of that, we can also say that 2 times the area of AC, now AC, we're talking about the square formed on AC, twice the area of AC would be AC, the area of AC, plus the area of EC. Okay? Now, by Euclid Book 1, Proposition 47, we've already established that the area that would be contained by line EA, now we're talking about making a square out of EA here, and one of the sides of that square would be EA, and then of course there'd be three other sides, and there'd be an area contained within those four sides. Okay? The area in the square EA would be equal in size to the area in EC plus the area in AC. Or we can say that twice the area of AC would be equal to EA. Okay. Now, we're also going to be able to say that because the length of FG, okay, right here, FG, let's go back over here, the area of the line FG is equal to EF, this one be right here, then we can also say that the squares that would be formed let's say we took EF here, and it was going to be one side of a square. We formed the other three sides and made a square out of it. Okay? And we did the same thing to FG. We took this FG and made it one side of the square. We made it three other sides, and boom, we had a square. So the square on FG and the square on EF would be equal. Okay? The areas in those two squares would be equal. Then we can go on to say that's twice the area contained by EF, which we're talking about the square on EF, would be equal to the area of EF plus FG. Okay. Now, remember we have an equilateral triangle, not equilateral, a right angle triangle. It starts at E, goes to F, and goes down here to G. And we're going to use Euclid Book 1 proposition number 47 again. The area contained by the line EG, okay, so let's say we're going to take EG here, and it's going to be one side of a four-sided square, and every one of the other three sides is going to be equal in size to EG. So the area contained inside of it is going to be equal in size to twice the area that was contained by line EF. So EF being one of the sides of a four-sided square, you make the other three sides the same size as EF, and the area contained by that would be 1/2 of the area contained by EG. Okay? Now, EF equals CD. Here's line EF here, and here's line CD here, and they are equal in size because of Euclid Book 1 proposition number 34. So the square on EG, which is this one right here, is equal to twice the square on CD. Alright. Now then, I will tell you more in my next video, and we will finally finish up this proof. Stay tuned.